And I appreciate all of you that have tuned in, and many of you are repeat attendees, and we certainly appreciate that. Today's webinar is centered on boiler room controls, but really not in the traditional sense wherein I'd be talking about controls and their respective functioning and their interrelationships. No, today we're going to be looking at controls, really I would think more whole before drilling down to the boiler room proper. Because the real focus will be on these modern day controls and how the data accumulated from them, how it can be leveraged for real true benefit. Now, you may be saying at this point, well, that's pretty intuitive, Steve. The data has to be monitored and it's leveraged all the time. Well, in actuality and reality, it really isn't, because many facility people and operators don't fully understand or appreciate the correlations with the data and how, when applied, can save energy and also sustain our finite resources while also improving, your uptime, the safety, and also the safety within the facility. So here's what we'll be covering today. Plant automation evolution. I'm going to touch on that just a little bit, and then monitoring control points. We'll then talk a bit about SCADA, the what, the how, and the why. Then the industrial process control system, the ICS, and how this links to the boiler room. And then we'll follow up and close with the leveraging the automated boiler control data for facility optimization. Now, I said we were going to start with a brief review of the evolution of plant automation and monitoring. And this is pretty much what I encountered when I first started getting into boiler rooms and control rooms about 45 or actually 50 years ago. And there's still some of those just like this out there today. And it's what is referred to as the boiler turbine boards and consoles, and including panels populated with various indicators and gauges. You'd also find manual auto stations, which allow the operators to individually access various control elements, and that would include strip or circular recording charts for documenting various pieces of data, such as pressures, the temperatures, draft possibly, all those kinds of things. And then writing this information into manual logs or just filing the strip charts or the circular charts into a file. Technology then started to advance, I would say, in the 1970s with the advent of the direct digital control, or DDC, control systems, which offered graphical interfaces which really mimicked the boiler turbine panel we just looked at, but offering easy-to-read digital displays. Now, the problem was that the operators were only able to view a small number of plant variables at one time, therefore not able to get a complete feel of the plant's, its overall operation. Well, then the 1980s arrived, and we started seeing the proprietary DCS systems, digital control systems, which replaced some of the now outdated technologies. Now, DCS systems offered expanded information and larger displays which better reflected the operator's tasks and duties. They were now able to see historical information, and its trending capability gave them a better understanding and grasp of the process and the facility's dynamics. These systems also provided higher resolution on the computer screens, and then the window feature allowed them more variables to be included on the screen at one time. This time also included the onset of what was referred to as operator knowledge and guidance systems, such as neural networks, fuzzy logic, which gave the operating staff the capability to monitor such things as heat rates, emissions, and boiler stack temperatures. The boiler stack temperature was then indicating possibly that the boiler is scaling on the water side, or maybe it's sooting on the fire side when the temperature elevated to a specific temperature, while the operating pressure, the ambient room temperature, and the firing rate remain constant. What was also evolving as we go through the 90s and then get into the 21st century was what I like to refer to as the separation of information into various buckets, which would be used to be very useful, I should say, to the various disciplines within the plant or the facility. For instance, those data pieces which were meaningful for optimized powerhouse operation were instantly available. Those things that impacted operations, be it products running at a given time, the line speeds, the quality rejects, the cartoning and the shipping of these products, or the data pieces which impacted maintenance, such as critical indicators for the cooling tower, for various pumps within the plant, ventilation fans, humidification systems, indoor air quality, all these kinds of things. Now it was possible for the facility to view its operation in a holistic fashion and then leverage the information for improved efficiency overall, not just in one area. Now, as this concept of discipline separation began to assimilate within various organizations, and remember now change is difficult, the SCADA system, or Supervisory Control and Data Acquisition System, that concept began to evolve. Now, this is a large-scale system of communication highways that tapping into various locations spread over large distances. Now, it's normally divided into three distinct categories, including industrial, infrastructure, and facility, in order to provide enough latitude to accommodate various business cultures. Now, for our purposes today, we're going to zero in on the industrial piece, looking at the industrial control system, which normally encompasses those areas I just mentioned, manufacturing, maintenance, and power generation. And power generation, or the boiler room, is of course our specific focus for this session. So let's go there and see how automation is impacting that area of the facility specifically. When we look at the boiler room, and then consider those areas within it which impact efficiency, sustainability, reliability, and safety, we need to consider a number of pieces of equipment. Certainly the boiler, but also its burner, the boiler feed equipment, the water softener, the dealkalizer, the chemical feed system, the economizer, just to mention the major ones. These all impact the facility's efficient operation, and I don't just mean fuel spend, and need to be properly controlled and monitored, with today's automation playing a significant role. We'll begin with the burner and those general areas which impact its operation. That is the burner management system and the combustion control system. Now, the burner management system is also many times referred to as the flame safeguard or programmer, because it's the device housed within the boiler's control panel, which is integrally wired into the circuitry to provide proper burner sequencing, monitoring, and lockout should the safe operation of the burner be compromised. It, too, as you can see, has evolved over the years from a tube type to electromechanical, then solid state, and that before evolving into the microprocessor based. But in all of its iterations, it still provided and provides the same basic functions. And those functions are what you see on the screen now. It manages the burner control and safety. It monitors. It proves pre-ignition interlocks. In other words, the proof of closure switch on a gas valve. It proves the burner blower motor is on. In other words, we've got combustion air. It proves that. It proves running interlocks and starts the burner cycle. In other words, it makes sure that we've got water in the boiler, all the running interlocks are closed and made. Otherwise, you do not advance. And then it starts the burner cycle. It proves pre-purge high and low limit. In other words, I've got adequate combustion air flowing through that furnace before I ignite, and then I'm at low fire before I begin my ignition sequence. It proves pilot flame. It proves the main flame. And it displays any burner-related alarms and forces automatic shutdown of the burner requiring manual reset. In other words, if we go out on a low water cutoff and the auxiliary trips, that's got to be manually reset. That's all monitored and controlled by your burner sequencing controller manager, the programmer or flame safeguard, as I mentioned. Or if we go out on high limit, that also has to be manually reset or you don't restart. So that's the burner management system. And then we have, what you see here now, the combustion control system, which includes those items on the screen. It's either got a traditional jackshaft control, as you see, or it might have parallel positioning with independent actuators controlling both the fuel and air. You could have O2 trim system. Well, I also mentioned that you could be cross-limited with your parallel positioning with cross-limiting. That means that the air, your fuel is always following air to keep you safe. You could have O2 trim included in the combustion control system. You could have the FGR, flue gas recirculation damper control, tied into this system if you're trying to control your NOx at a low level. Variable speed drive could be tied in. This is all part of your combustion control system. The draft control could be integrated. Feed water control, lead lag control when you have more than one boiler and you're sequencing those on and off. And then full metered control of both fuel and air. All that is combustion, part of your combustion control system. All right, this is all well and good, but as far as combustion control and other monitoring going on, which impacts the boiler room operation, how do we reach out and get this information? Well, that's what you see on the screen now. We have various devices which are needed to acquire and send data through a communication highway or a computer bus network. Now, as far as the devices themselves are concerned, the transducer is a device which converts one form of energy to another, let's say heat to a millivolt signal. The thermistor is a type of resistor whose resistance varies greatly with temperature, much more than other standard resistors. Then we have the traditional thermocouple, which converts temperature to a low voltage signal. We also have the RTD, which again is a temperature sensor converting those variances in temperature with variances in resistance, which is measured in ohms, and then converts this to an electrical impulse such as a 4 to 20 milliamp signal or a 0 to 10 volt signal. These RTDs are slowly replacing thermocouples. And lastly, we have the transmitter, a telemetry device for converting measurements from a sensor into a signal and then sending that signal through wires to a receiver such as a controller or a display. Now, as an example, here you see flow meters for both water and steam, which measure forces produced by a flowing stream as it overcomes a known constriction, such as an orifice, to indirectly calculate flow. Or the flow measurement is a result of a specific velocity over a specific area. But in either case, the transmitter converts the mechanical result into an electrical impulse, which is normally a 40 to 20 milliamp signal, and then sends this to a loop controller or a PLC, which may be controlling, let's say, the firing rate on the boiler based on steam demand. Okay, so now we have these signals coming from various sensors and transmitters across specific channels or highways. Let's now look more closely at where they go. And the two very common receivers we'll be looking at today, and as I just mentioned, are the loop controllers and the PLC or programmable logic control platforms. Now, here is what you see on the screen now are loop controllers, serving various operating functions in and around the boiler. Now, these are excellent devices and serve a very useful purpose in controlling and monitoring many functions. But they do have many disadvantages, which you can also see. First of all, they're individual components with no interrelationship with the other controllers. They require a separate panel for mounting, and then considerable factory and field wiring for interconnectivity, to say nothing about the tuning expertise that will be required in the field. Now, contrast this with the PLC-based system, which has all the functions I just showed you, neatly wrapped, however, into one complete package, all pre-programmed and wired at the factory. For instance, Through a PLC-based master panel, multiple boilers can be appropriately monitored and staged online to satisfy any varying load condition. Now, it's referred to as lead-lag control and can include such features as automatic boiler rotation, equal runtime on the boilers, lead-lag modulation of the boiler's burner, or unison firing, where they all fire at the same rate once they've come up to temperature. The other feature which may be incorporated in the PLC package may be oxygen trim, where we're trimming either fuel or air to maintain the proper fuel-air ratio. That would be depending upon the varying climatic conditions. Or maybe we are incorporating parallel positioning of the fuel-air mixing devices using independent actuators and possibly including variable speed drive on the combustion air fan motor. Or maybe we have an automatic draft control. That would be incorporated into the PLC logic, which automatically adjusts the draft in response to changing conditions in the stack and breaching. Or we have modulating feed water control based on steam demand and reduced or increased firing rate. And we want to incorporate and monitor that for chemical treatment assessment purposes. I mean, the possibilities are endless. And they just require the knowledge of need on the part of the owner, and then couple this with knowledgeable suppliers who understand the need and can supply the software and hardware required to do the job. And by knowledgeable, I mean a supplier who not only understands the engineering from the electromechanical perspective, but also the code and standard requirements, which, if violated, can adversely affect the customer. You know, things like understanding the NFPA 85 standards, which state very clearly that the burner management system and combustion control systems must be separated, though they can be integrated into the common PLC platform. Okay, so we have an industrial control system in place, and we're concentrating on the boiler room. And most systems we're seeing today are PLC-based platforms. So we'll look at those and start with the typical status overview screen that we will find with these PLC platforms. It starts with the boiler ID, which is the boiler number that would be assigned by the customer, and then its serial number. It also includes its runtime in hours and the number of cycles during that period. Very important. You'll also find other very useful information, such as the fuel being burned, the combustion air temperature, the oxygen level, the stack temperature, the operating pressure, the firing rate, the feed water temperature, all of these things, all very, very useful pieces of information. And we'll be talking about them again in a few minutes. You'll also find some control buttons at the bottom of the overview screen, which will allow you to toggle to individual screens, such as the burner management screen. This shows you the status of all the running interlocks, and if there is a failure, which circuit or the terminal number, which one failed, totally expediting fault diagnosis and mitigating downtime. These faults are also stored and can be easily pulled up and documented for prevent maintenance reasons in the future. You can also call up the firing rate control screen, which is the setting of the modulating control on the boiler and spans a range which is within the burner's turndown capability. Now, note in this case on the screen, the burner is operating at about 25%, so it's in low fire, and it's rating at sea level. And it's got O2 trim, so it also includes that particular value on the screen as well. In this particular case, it's 6% at low fire. Again, all very useful information that can be called up. Okay, now we have a very intelligent system. It's giving us all sorts of useful information. So what do I do with it? How do I leverage it? For example, we can get various boiler pressure points, such as the draft pressure, steam pressure, the feed water pressure, my fuel pressures, and my combustion air wind box pressure. Or we can retrieve flow data, such as fuel flow that could either be gaseous or liquid. We can get our combustion airflow, our steam flow, our continuous blowdown flow for controlling the TDS levels in the boiler water. Our blowdown heat recovery flow and our feed water flow are all measurable and very important data pieces. And then there's a closer look at the boiler's feed water, showing things like condensate return, flash steam recovery, deaerator and surge tank drum levels and pressures, and the boiler feed pump pressures. And then lastly for this discussion, we have other relevant temperature data pieces which are critical when evaluating boiler efficiency, such as the economizer inlet and outlet temperatures, both on the fire side and the water side, feed water temperatures and boiler water temperatures, oil temperature if you're burning heavy oil, the outdoor temperature, and of course the indoor temperature. All of these data points can be easily retrieved, stored, and then trended to provide you with some of the options cited, such as, that would be if you have some of the options cited, such as an economizer or if you're burning heavy oil. But all this information can be accumulated and analyzed. All right, now I have all this information tailored to my specific needs, and how do I leverage it? How do I maximize the information, or better yet, how do I correlate the information into meaningful data sets? Now, last month during our webinar covering the proper boiler room assessment, we covered the subject by using the 4 cornerstones as our basis for achieving total optimization in a process facility. As you see, it's efficiency, sustainability, reliability, and safety as the cornerstones. And when we talk about leveraging the data coming from an advanced industrial control system, these cornerstones will be considered and impacted. All right. So what are some of the data sets that we can easily capture and then correlate for facility benefit? I'm going to start with steam flow versus fuel flow. Leveraging this comparison starts with the knowledge of the cost of fuel. Now, whether it is dollars per gallon of oil or therm of natural gas or decatherm of natural gas. We then document this value against 1,000 pounds of steam per hour to arrive at a cost per 1,000 pounds of steam produced. Now we can then go out into the system and look for energy losses. Losses like steam traps blowing through or not operating properly, pipes which aren't insulated, or steam leaks. You know, remember from last month what I showed you relative to steam leaks. In this case, the cost per 1,000 pounds of steam was $7.50, and a 1/2 inch leak in that pipe under 100 pounds of pressure resulted in almost $56,000 per year in losses. 1/2 inch opening in a 100-pound backed pipe. Then we have the correlation of steam flow versus drum level. Remember, for each pound of steam you evaporate a pound of water. And there's 8.3 pounds in a gallon. Now, when we see steam flow and pressures remaining constant, and consistent, but we've had a rash of water level fluctuations and possible outages, you know, it's time to check the boiler's water chemistry for imbalance causing some foaming and/or fluctuations in surface tension, the rise and fall, the sink and swell of that water level. Now, the foaming can cause carryover and wet steam delivered to the process. And of course, the outages caused by low water are an interruption to production. Now, both of these maladies can cost the facility hundreds, if not thousands of dollars in a very short period of time. Or how about the drop in feed water temperature from the normal reading of 227 degrees coming out of my deaerator has trended over several months, but it drops to 200 degrees. Big red flag goes up, as this is indicating either the steam PRV feeding the deaerator is malfunctioning, or possibly the high and or low pressure condensate, which can also be monitored, is not at temperature or not returning at all. In any case, this is a significant energy loss, as for every 10-degree drop in our feed water temperature, we lose 1%. So in this case, in this scenario, we've lost over 2%. Then there's the case where we have steam flow at normal levels, but the pressure in the header is decaying at unpredictable times. Steam flow at normal levels, but the pressure in the header is decaying at unpredictable times. You know, we had a situation like this with one of our customers. And after several trials and error with changes to many of the boiler's operating set points and parameters, by the way, they had a lead lag system with PLC-based controls on the boilers, steam and water flow meters were installed in the system and tied into their industrial control system. Bingo, the answer. Someone wasn't following procedures and indiscriminately performed CIP during heavy production periods. This instantaneous steam demand caused the pressure to drop, robbing valued steam from production, costing significant product loss. Now here's another very important data comparison. Stack temperature versus operating pressure and firing rate. Stack temperature versus operating pressure and firing rate. Okay, these are the base points. Keep that in mind. These data points should be gathered, stored, and routinely evaluated. Because depending on the turn down of the burner, say it's a 4-to-1 or a 10-to-1 turn down, each firing point should deliver a consistent efficiency if the operating pressure is the same, the burner is in tune, and the boiler is clean on the fire side and the water side. Then, for every 40-degree increase over that particular data point, increase in stack temperature, we lose 1% in efficiency. Note the red arrows, with everything remaining constant except the stack temperature. You can see we've gone from 300 net to 340 net, and we've lost 1%, 82.3 versus 81.3. And all this information I was just talking about is on that PLC-based platform and the overview screen. So when we see that stack temperature elevating, it's time for us to say, wow, we got to look at something here. We've got to shut this boiler down when we can, and we have to look at the fire side and the water side and make sure that it's clean. And if it isn't, it's got to be taken offline and cleaned, or you're going to be losing that 1% for every 40-degree rise. And the last pieces we'll be looking at today as far as data sets is to leverage change and improvement based on oxygen content in the stack versus the firing rate. And that's what I was just stressing to all of you before when we looked at that overview screen and then that chart showing the increase in stack temperature. In the slide that you see on the screen now, the curve indicates the typical profile of excess air or oxygen. And just so you understand, there's a correlation between the two. Excess air and oxygen are interchangeable. 15% excess air, for instance, is the same as 3% O2 or oxygen. So this is in the flue gas as the burner modulates from low to high fire. In other words, what I'm saying here is that as you modulate from low to high fire, the excess air is going to increase, and it climbs. Now this is normal. And you know, when the technician tunes the burner, he tries to keep this value as low as possible while maintaining flame stability at the lower levels. So 6 to 8% oxygen at low fire is pretty common. Now there are burners out there that will hold 3% throughout the entire turn down. But for the most part, many burners out there won't. You'll see 6 to 8% at low fire. Point is, these values of excess air versus firing rate need to be captured and monitored. Because as you see in this slide, as we increase the excess air over the desired set point, we lose efficiency. We lose 1% in efficiency for every 2% increase over the desired setting. Now this is why O2 trim systems are installed, because they keep the burners properly tuned. They're not going to tune your burner, but if it's properly tuned, it keeps the fuel-air ratio in check when there are climatic condition changes. And conditions change, as you can see in this slide, with ambient air variances. We went from 80 degrees in the boiler room and 15% excess air, or 3% O2, at startup, to 20% excess air when the boiler room temperature dropped to 60 degrees. The air got denser. And then when it increased to 100 degrees, very typical in boiler rooms, we dropped our excess air to about 10%. Now, these condition variations are wasteful and they're possibly dangerous if the O2 trim system is not employed to compensate. But in any case, the correlation between oxygen or excess air in the flue gas and firing rate are important data points to monitor. So now we have almost limitless information that we can capture within the boiler room, and covering essentially all the equipment on the boiler and its supporting accessories. And then through a communication bus network such as Ethernet, DeviceNet, BACnet, and so on, it can be sent to various receivers to see on the screen that you would see on the screen now, I should say, and used by the various disciplines within the facility which may be impacted. And you know, if electronic filing is not desired or it's not appropriate for specific activities, the information can be dumped to a printer or a data logging system, and also an alarming system if necessary. And it can even tie into the building automation system if that's desirable and helpful to the customer or the end user. Then in a multi-plant operation, possibly covering various locations around the state or nation, the information can be sent to the proper individuals within the organization through the SCADA system. Now, this could include operation and maintenance VPs, your energy czars out there, sustainability managers, the safety chiefs, so on. They go to all of these people so they can begin to formulate a plan and try to optimize the organization as much as they possibly can. Then this information is leveraged, not only for the specific site, but then globally for overall company improvement as it relates to efficiency, sustainability, reliability, and safety. And lest we forget, shareholder equity. So as far as the takeaways for today, before we get into the Q&A, this is what I would say they are. Today's advanced industrial control systems allow the powerhouse maintenance and operations to collaborate and share information. And by the powerhouse, of course, I'm talking about the boiler room operation. SCADA systems tie in and allow this information to be transmitted globally. So now we've got a very holistic global view of what's going on as far as our energy conservation is concerned, the reliability of our plants, the sustainability of the finite resources, and of course the safety within our facilities. The burner management system controls and sequences the burner. That's what it does. The combustion control system controls other related functions such as fuel and air metering, feed water metering, draft control, motor speeds, and so on. The burner management system and the combustion control system must be separate per NFPA 85, though they can be integrated on a PLC platform. Motor control and monitoring can be through loop controllers or a PLC-based platform, which is becoming the PLC, becoming the preferred method because of its high degree of integration and the ease of field install. The PLC-based platform can be expanded to include various controls and sensors for capturing valuable data, for leveraging the plant optimization. And lastly, this information should be logged and trended to maximize fuel efficiency, sustainability, reliability, and safety in the plant, and then throughout the entire organization. So with that, I believe that we're ready for some questions, Susan, so take it away.
Thank you, Steve. Thank you very much. Okay, I have stopped the